Hello, this is Professor William Mather, and welcome to Embracing Randomness. This episode is all about computing with coin flips. Even though some people try to avoid randomness, did you know that you can compute with randomness? In fact, randomness can be a very powerful computational tool. To ease into this, let's first ask, what can you learn from coin flips? Go find a group of people. 20 to 30 people is a good size, but smaller groups will work with some creative thinking. Make sure everyone has a coin with a head side and a tail side. You might want to practice flipping or spinning this coin to get a random outcome of heads or tails. I'll assume flipping. See the Wikipedia page below if you want more information. Now, for a fair coin, we expect that half the time a coin turns up heads, and half the time the coin turns up tails. Let everyone in your group flip their coin and by a show of hands count how many flips are heads. Chances are that you find half the flips were heads, give or take a few heads. If you check this one or two more times, you'll find that you get a slightly different number of heads each time, but the number is still close to half of the total. Let's test whether or not coin flips care about one another. Now everyone in your group flip their coin twice and remember the outcome, such as HH, heads then heads, HT, heads then tails, and so on. What did your group find? Chances are that each outcome is equally likely, with each occurring about 1/4 of the time. One way to think about this is that finding a heads or tails on your first flip doesn't influence the chance of finding a heads or tails on the second flip. Continuing this argument, seeing several heads in a row doesn't make a tails more likely. This makes certain outcomes that don't look random much more probable than people realize. You can see this for yourself. Find a group of people, larger is better, but 20 to 30 is good enough. Give everyone a coin, and everyone flips coins until one person gets 6 heads in a row. Will you have to wait forever? The answer is no, and let's see why. So let's reason this out. What is the chance that you get a heads on the first flip? This is 1 out of 2, or 1/2. What is the chance that you also get a heads on the second flip? As we have seen, this should be 1/4. Continuing down this line of reasoning, you can show that the chance to see 6 heads in a row is 1 out of 64. Not especially big, but definitely not small. In a group of 20 people flipping 6 times each, we then predict that about 1/3 of the time, at least one person will find 6 heads in a row. Now we're talking about a serious chance of this happening. And an exact calculation gives a similar answer. A group of 20 would find 6 heads in a row about 1/4 of the time. If the group of 20 repeats 6 flips 3 times, our simple estimate and an exact calculation both predict the group is more likely than not to find 6 heads in a row. So to answer our question, you shouldn't expect a group of 20 to have to flip more than about 18 flips per person before someone finds 6 heads in a row. So now that you're an expert coin flipper, let's compute with coin flips. Computers need numbers, not heads and tails, so imagine that heads are 1s and tails are 0s. On a computer, we call these bits. Here is how you create your very own random number from coin flips. You might want a calculator. A recipe using 5 flips is to 1. Start with a number, we'll just call this Q, and set it equal to 0. Flip a coin. If it is heads, add 1 to this number. Divide this number by 2 to get a new value for this number, and repeat steps 2, then 3, 4 more times. What you should find is a number with roughly equal chance to between 0 and 1. The amazing thing is that just about any other kind of random number you would want can be generated by these standard random numbers. You can use your random numbers to compute many things. For example, let's estimate the mathematical value of pi. So use the recipe to generate 2 different random numbers, q and w. Now each person compute q times q and write that down, and then compute w times w and write that down. And now in your group, count the fraction of people who find q times q plus w times w is less than 1. As it turns out, this is actually an estimate for pi divided by 4, so if you multiply the fraction of people who found q times q plus w times w is less than 1 by the number 4, this is actually an estimate for pi. So let's try this out on a computer first, and then you try it out in your own group. What I found was a simulation with 20 people generated a value of pi over 4 of roughly 0.85, and with 400 people it was about 0.7975. So this actually compares nicely to the exact result of pi divided by 4, which is roughly 0.785. So why does this work? So your random numbers actually explored the blue box in this picture, and when people found that q times q plus w times w was less than 1, it actually finds points within this red region of this plot. And so it turns out that the ratio of the area of the red region to the blue box is pi over 4. This can be shown by geometry, but we won't do this here. So, thanks again for watching Embracing Randomness, a project supported in part by the National Science Foundation and done in collaboration with Kids Tech University. And I'll see you next time, and remember, stay random.